Good morning, students. Let's continue the topic valence bond theory because we have already discussed few of the property in the previous video. So as we discuss about the types of ligand, there is the three types of ligand we will discuss in the previous video: strong ligand, weak ligand, and average ligand, and the example and their property. How can we find out the properties of the complex compound, like it is the diamagnetic or paramagnetic, what will be the spin multiplicity, what will be the geometry, so on. So write down the next point. As we know, so in the case of wave, in the case of this particular compound FeCN6, we know that cyanide is a strong ligand, strong field ligand, and it approaches very fast to the metal ions. The inner electron present in the metal ion suffers repulsion. Present in the metal ions suffers repulsion. Due to repulsion experienced by the incoming electron from cyanide ligand, they get paired up. That is the reason, due to presence of strong ligands, the unpaired electron present in the central metal atom get paired up, because strong ligand has tendency to pair the unpaired electron. Next example, we take the weak field ligand. Suppose we have, next example is FeH2O6 and 3+. So write down the configuration at first. Fe, we know that 26. So argon 3d6, 4s2 and 4p0. So in this central metal atom is a +3 oxidation state. So argon and 3d5, 4s0 and 4p0. So 3d 1, 2, 3, 4, 5, and total 1, 2, 3, 4 and 5 unpaired electron present in the d orbital, and the s orbital 4s is empty and 4p is also empty. As we know, H2O is a weak field ligand, no pairing of electron takes place. In that condition, how can we find out the hybridization? So next way, in the 4th cell there is a 4d orbital is also present. So 1, 2, 3, 4 and 5. So 4d is also available. In that condition, the total formation of S of triangle geometry sp3d2. So total number of 6 water molecules occupy 1s, 3p, and for D2, sp3 D2. So what will be the hybridization, and let's find out the total characteristic about this hybridization. Page sp3 d2 magnetic moment, magnetic moment. So mu equal to unpaired electron. How much unpaired electron? 5, and 5 plus 2 Bohr magneton. So 35 Bohr magneton. What about the spin multiplicity? Spin multiplicity. Spin multiplicity, the formula of spin multiplicity is 2s plus 1. So 2, 5 by 2 plus 1. So total 6. Total 6. And what will be the nature of this particular compound? Due to unpaired electron, the nature is paramagnetic. On this basis, you can find out all the information about the complex. At first, find out the given ligand is strong and weak. On this basis, you can simply find out the nature of particular complex compound on the basis of this. Suppose another example. Suppose number 3. So we take NH3 and 3 plus. As we know, this is also a strong ligand because we already discussed about the ligands, other ligand which act as both weak as well as strong. So let's find out the hybridization on the basis of configuration 3d7, 4s2 and 4p0. Here cobalt is plus 3 oxidation state. So write down the configuration 3d6, 4s0 and 4p0. 2 from here, 1 from here. So 3d6 configuration. So 3d, 4s and 4p. 4s, 3d6, 1, 2, 3, 4, 5 and 6. As the NH3 is a strong field ligand, so pairing of electron will be takes place. Strong field ligand, so pairing of electron takes place. Pairing electron takes place. In that condition, this comes into and this goes into this. So we can find out the two, 4 and 6. This is 3D and this is 4S and this is 4P. So the hybridization will be D2sp3. So hybridization will be D2sp3. So all the information, spin multiplicity because there is no unpaired electron, so spin multiplicity will be 1, and the magnetic moment will be 0 because there is no unpaired electron, and all the electrons are paired up, so the nature of this particular complex compound is a diamagnetic. So hybridization D2sp3 and nature diamagnetic and spin multiplicity So its multiplicity equal to 1 and magnetic moment mu equal to 0 because there is no unpaired electron. And so valence bond theory is very important, very important for the examination point of view. So let's see. Compare the, at first write down the shape or geometry, then hybridization, then involvement of d orbitals used, and example. Suppose number 1, octahedral. Hybridization may be D2sp3 or sp3 d2, and involvement of d orbital d x square minus y square and d z square, and the example is SF6 because their geometry is octahedral. We know the geometry of octahedral like this: 1, 2, 3, 4, like this, and one from here and one from here. So this way you can draw the geometry of octahedral, and as we know, the bond angle of this particular, this is called the axial, this is called the equatorial. So the bond angle between axial and equatorial is 90 degree. Next we discuss the square planar. DSP2, and the involvement of d square and y square, and the example is PTCl4 square planar like this. PT 1, 2, 3, 4. This type of structure takes place. Next is a trigonal bipyramidal. And sp3d or dsp3, involvement of dz square, and the example CO5, and we know that the structure like this. Trigonal bipyramidal. So on the basis of this we can easily find out the geometry or the hybridization of given compound. So next we discuss the crystal field theory. Next topic is crystal field theory, CFT. And at first we talk about the octahedral complex. So CFT for octahedral. Crystal field theory for octahedral complex. So following are the main points. points. Number 1. This theory considers only electrostatic attraction between the ligand and the central metal atom. Number 2, it considers the ligands and the central metal atom as point charges. Means central metal atom is positive point charge, and the ligand is negative point charge. Number 3, attractive forces decreases energy of system, increases. Attractive force decreases energy of the system and repulsive force increases the energy of system. Attractive force decrease the energy of system, repulsive force increase the energy of system. To form complex compound, number 4, to form complex compound, negative charge ligand molecule approaches positive central metal atom. So let's we discuss how this is happened. At first we discuss about the for the octahedral geometry. At first we discuss about the octahedral geometry. Crystal field splitting theory for octahedral geometry. So octahedral. So we all know about the octahedral geometry, like so students, here two types of bonds are present. Two types of bonds are present. First we called axial and This is called the axial bond, this is called the equatorial bond. So axial and equatorial, for every perfect axial bond equal to equatorial bond, means two bond lengths are should be equal. For every perfect octahedral complex, means bond length should be equal. Bond length should be equal. All bond lengths is at the angle of 90 degree. This 90 degree, this 90 degree, this 90 degree. So all bond lengths are equal. Next one is if bond length, we talk about the bond length, if axial bond length is greater than equatorial, the geometry will be trigonal bipyramidal. Trigonal bipyramidal. We all know the geometry of here. The axial bond length is greater than equatorial bond length. Next one is if axial bond length is less than equatorial, the complex will be pentagonal bipyramidal. Like this. Suppose 1, 2, 3, 4, 5, 6 and 7. So 1, 2, 3, 4, 5, 6, right? This is called the pentagonal bipyramidal. All the position is appropriate. Ligands are present. So let's we discuss the types of orbital. There, at first we get the concept about the EG. EG is doubly degenerate, and it is from dx square and y square and dz square lie along the axis. We all know the structure of, suppose this is x, this is y, this is j. Dx square, y square, and y square, like this. And dz square, x. Suppose this is x, this is y, this is z. So this type of structure formed. So this is x square, y square, and this is dz square. These two orbitals are known as EG, means doubly degenerate orbital, and T2G, triply degenerate orbital, in which out of 5, 3 are known as T2G, dxy, dyz, and dxz. It lie between the axis, dxy, x, y and z, dxy, like this. y and z, dx y, and second is like this. This is dx y, x, y and z. It lies between y and z. So y and z, and second one is like this. So it is called the dy z dxz, x, y and z. Dxz means between this and this, like this, not on the y-axis, between this, like this, x, y and z. So this is dxz. So out of 5 orbitals of d, 2 are known as Eg. Which one? Dx square y square, dz square, because it lies along the axis. And out of 5, 3 are known as T2g, dxy, dyz and dxz, because it lies between the axis, not along the axis. So let's we discuss. Suppose we take Mn6 type coordination compound, means M is center metal, L is the ligands, and coordination compound. So as we know, octahedral geometry, like and all the position is ligands are present, and the here is the central metal atom. And what will be the hybridization? It may be sp3d2 or d2 sp3 maybe, and d orbitals involved. We know that in octahedral geometry, d square y square and dz square. To make sigma bonds, ligands will approach along the axis. So along this axis, there will be maximum repulsion. Between metal electron and ligand electron. So sigma bond is formed by head-on overlap of two orbitals. For octahedral structure, we denote we denote it by delta naught. So let's we discuss. This is the d orbitals. When no ligands approaches, this is called the degenerate because all of them have equal energy. So this is the degenerate orbital. Degenerate orbitals. When ligand approaches, divided into two parts. 3 orbitals on the lower sides and 2 orbitals on the upper sides. So this is known as EG and this is known as T2G, triply degenerate orbital and doubly degenerate orbitals. These 3 R's are dxy, dyz, dxz, and this is dx square y square, and this is dz square, and this is dxz, dyz, and dxy, dxy, dyz, and dxz. And so, and it is represented, this is called the energy gap, and it is energy gap of EG and T2G. It is called the crystal field energy gap. Crystal field energy gap, we call it. Energy gap between T2G and crystal splitting energy between T2G and EG. So there is an energy gap between this, and it is represented by delta naught. Crystal splitting energy gap is denoted by delta naught. So in the octahedral case, when the ligand approaches, there is a splitting of the degenerate orbital takes place. Half goes upper inside and two goes upper inside, 3 comes in the lower side. So the 2 orbitals which goes on upper side has high energy in comparison to T2G, means 3 this orbital. So let's we discuss about the energy when the degenerate orbital, in this all the orbitals have same energy, but when this split on the presence of ligand, in case of octahedral, T2G has less energy than the EG. And how much energy, how will we calculate the energy of this particular orbital? For this we consider this particular is a average. So we take a mean point from this, and it is called the barycenter. Barycenter. We take as a barycenter is a 0. Barycenter is a 0 because we consider this particular is a mean point. So we calculate this particular 5 orbitals, how this orbital takes energy and goes upper, and how much energy taken by this T2G and goes in the downward. So total splitting, how will we calculate? So it comes the upper side. So experimentally calculated 0.6 delta naught, and here minus 0.4 delta naught. So T2G is orbital, the average of T2G and EG orbital, we call it as a barycenter. So calculating it, suppose 0.6 plus 0.6 how much orbitals? So into 2. So it comes plus 1.2 delta naught and minus 0.4 delta naught into, here also delta naught we use, into how much orbital? 3. So it comes minus 1.2 delta naught. It is D2G, it is D2G and it is EG. So average comes, plus 1.2 minus 1.2 equal to 0. So in this way we can calculate the energy of the particular orbital. So now the factor to be multiplied to number of electrons to calculate the crystal field splitting energy are minus 0.4 delta naught for T2G electron and plus 0.6 delta naught for EG electrons in the octahedral complex. Both are equal and average becomes 0. So both are equal and average becomes 0. Now note down the next point. The more strong filled ligand, more electronic repulsion, thus more splitting of the orbitals, d orbitals. So splitting of d orbitals will depend on the ligand, field strength. Delta naught also depend on oxidation state of metal. Higher the oxidation state of metal, hence higher electrostatic attraction and higher electronic repulsion, and as a result higher splitting of orbital. This is the case for the splitting of the orbital. Suppose we have 5 degenerate orbital, 1, 2, 3, 4, 5, and in one case, so this is EG and this is T2G. So here the splitting of octahedral complex takes place in one case. In another case, suppose so we can say here splitting of, this is EG and this is T2G. So here the splitting is large and here the splitting is large and here the splitting is small. It happens due to presence of weak field ligand and it is happened in the presence of strong field ligand. So strong field ligand, in the presence of strong field ligand, splitting will be more. In the presence of weak field ligand, the splitting will be less. So we can say that crystal field splitting energy in the case of octahedral when weak field ligand, so delta naught is less than pairing energy, and high spin complex, and this will follow Ohm's rule. And we calculate the energy plus 0.6 delta naught into A plus B into minus 0.4 delta naught. A is the electrons in Eg and B electrons in T2